Worksheet 9B, also shear and moment diagrams. All today is shear and moment diagrams. Calculate the support reactions and draw the shear and bending moment diagrams for the beam. Load is shown, and in this case, a cantilever, as you can see, the fixed support on the right, similar to example 3 in there that we done before. So here, find the external reaction, very important. And I give that to you to figure it out. Use in your engineering, mechanics, statics knowledge. If not, you cannot, then go back to review that to the equilibrium. So 40 Newton, if you sum up on the force in y direction, you have that the vertical reactions at the fixed support, it will be 40 Newton. And you can see that the couple moment 100 Newton meter on the left, and that is clockwise, and the 40 Newton also create a couple at the fixed end. It 40 in the middle time 10, so it will be 400 Newton meter, and that about the fixed end it will be counterclockwise 400 Newton meter plus the plus 100 Newton meter clockwise. 400 Newton meter clockwise, counterclockwise, plus 100 Newton meter clockwise. So it will be the net. It will be 300 Newton meter counterclockwise for the total axonal moment applied. So the reaction at the fixed end, excuse me, for the moment, it had to be the same in terms of magnitude, but the opposite direction. It counterclockwise. 300 Newton meter. Then the reactions here have to be 300 Newton meter, but it will be clockwise. And again, if you're not sure and it know the components, no force components at the fixed end in the y direction, if the sum up on the force in x direction, it will be equal 0. So keep that in mind when you do the axonal support. It's very important. You use different equations to check whether your answer is correct, and I give that to you for that review. Now go back to draw the moment and shear and moment diagram. So first start with shear, and always start with from left and start with 0. So from 10 meter, the first 10 meter, nothing about shear. The couple at the left, it nothing to do with the shear diagram, as you can see. So it's nothing. The shear, it will be 0. 0. So basically, if you recall, the first 10 meter from left, that is the pure bending. Only create the internal bending moment that you will see it later, but not shear, internal shear in there. There's nothing in there that affect, no distributed load, no concentrated load between the first point 10 meters on the left. And then go to the middle, 400 Newton going down. So create the continuity on the shear diagram and move down 40. So it will be 40 move down because load move down. And then it nothing in the last 10 meters. So you have horizontal 40. And then have 40 Newton go up. So create the discontinuity in the shear diagram, move up 40 Newton. And they stop at 0. And that's what we have for the shear diagram, right? Start from left 0, close, and have to be 0 on the right side. And from that we have to continue with the moment diagram. And in this case, just go ahead to find out the areas. Of course, the first part, you can see the also straight line, and it's 0, so it's no areas. That one equal to negative, let's see, negative 40 times 10, so negative 400 Newton meter for the area under the shear curve for the second 10 meter. So from that we can go ahead to draw the moment diagram. Start at 0 again, start at 0. Have a couple 100 Newton meter 100 Newton meter, and it caused the discontinuity on the moment diagram, and in this case the couple 100 Newton meter, as you can see here, that either clockwise, then based on the designer side convention, clockwise couple apply for the external couple, it will create a move up discontinuity, but move up in the moment diagram. So you have that one here, move up 100 Newton. And then between the left and then the 400 Newton, the first 10 meter, it no other thing that will affect the moment, because you see the areas under the shear curve is 0, because the shear in that 10 meter is 0. So it no change in moment. So the moment here remain unchanged for 100 Newton meter. Okay, and then we continue. You see 100, and then we have the change between the last two, the last 10 meter is negative 400 Newton meter. So it will be 100 Newton going down negative, so it will be go to the 300 Newton meter to make the chain 400 Newton meter. 100 positive, 300 negative, total in terms of magnitude the chain 400 Newton meter negative. And make sure it whether it's parabola, straight line, or cubit. So in this case, no distributed load, so you will have a straight line for the moment. Or you can say the shear between the 2 points, so 10 meter, the last 10 meter is the same, negative 4 Newton. So the slope, it will be the same. When the slope the same, it will be straight line. So you will have that here, straight line, and going down there. 0. Not enough yet. We have to close, right? 0. So here you have a couple clockwise 300 Newton meter, clockwise 300 Newton meter, clockwise couple. It will create the discontinuity in the moment diagram, and it move up. So you will have it move up from negative 3, move up 300 Newton meter due to the couple reaction 300 Newton meter on the fixed ends, and from that it will be 0. So you see, start, if we do correctly, it have to start at 0 and finish at 0 for both shear and moment diagram. And now we can go ahead to put the straight line there. It is straight line and this straight line, and slope on the last 10 meter on the shear is equal to the shear at that point. And as you can see, it will be negative 40, negative that way, slope going down 40 Newton. Slope in the first 10 meter equal to 0 because the shear equal to 0 in there. That way it horizontal, as you can see for the moment diagram. So from this you can see the maximum shears equal to 40 Newton. The maximum moment equal to 300 Newton meter, and it will be at the fixed ends, as you can see from diagram. So diagram, shear and moment diagram, to know where is the most critical point that you design, where is the greatest shear and where is the greatest moment located along the beam. So that is worksheet 9B.